Well, here we are at the end of this course on computer vision. We have covered a lot of material, from the geometry of image formation to the recording, representation, and manipulation of digital images, the analysis of still and moving images, and a myriad of tools for image understanding. We have, of course, not covered all of the materials in the field of computer vision. It's my hope, however, that we have provided you with the skills and the scaffolding to fill in whatever gaps we may have left. It's also my hope that you'll be able to utilize the various numerical tools in applications that may go beyond computer vision. From basic least squares estimation to artificial neural networks, the numerical tools that we have discussed have broad applications to many problems in science and in engineering and in the social sciences. When building a computer vision system, you'll have to make a number of decisions, from how to record the images, how to represent them, and how to analyze them. The most critical issue in making these decisions is understanding the requirements of your system in terms of performance and efficiency, and understanding the underlying assumptions that go into the choice of your tools, and of course, then evaluating and refining your system. This latter step of evaluation and refinement is critical, because no matter what you build, it will have to undergo multiple iterations. And here is where there's some tension between the power of different techniques and our ability to understand them. In particular, there is a tendency today in computer vision, and really in many other fields, to just unleash artificial neural networks on every problem. This machinery, after all, is quite powerful, and it's a relatively easy to achieve what would seem to be good results on just about any problem. The trap, however, is that these neural networks are nearly impossible to fully understand. And when the network fails to correctly classify an image, it can also be nearly impossible to understand the reason for this failure. The usual response to performance issues is to throw more data at the network. But labeled data is not always easy to come by. And with networks growing in size and complexity, the data demands are becoming increasingly more burdensome. In addition, neural networks often struggle to generalize to novel data sets that deviate even slightly from the training data. That's not to say that there isn't a time and a place for neural networks, but in my view, they should not be the tool of first resort. They should be the tool of last resort. My advice is to start by understanding your problem. Be explicit as to what assumptions you need to make. And don't worry about making aggressive assumptions if they simplify your problem. Then, bring to bear the minimal set of tools you need to solve your problem. From there, you can begin to relax your assumptions and slowly and carefully introduce more complex techniques to solve the increasingly more complex problem. Finally, and really importantly, while there are many exciting and impactful problems in computer vision, great care must be taken to consider the ethics of the tools we develop and potential bias in any of those tools we develop. Computer vision systems today can be used in ways that their creators may not wish or even have intended. For example, I was recently talking with a researcher whose earlier research from decades ago was instrumental in the development and deployment of modern facial recognition systems. This researcher was horrified how his technology has been misused for surveillance and privacy-invading applications. This researcher was also horrified to see the racial bias in facial recognition that persists today. He said that in hindsight, these problems were somewhat predictable, but nobody was thinking about these potential misuses decades ago. We need to think about these issues. We need to think not just how to do something, but if we should do something. We need to think about how to put proper safeguards into our technology to mitigate potential harms. And we always need to be aware of how bias can slip into our technology. If the past 2 decades have taught us anything, it is that with great power comes great responsibility. By all means, I encourage you to explore great ideas, innovate, and expand our boundaries of knowledge. Take care, however, to make sure that you don't unintentionally do more harm than good.